Have you ever considered how something can be two seemingly contradictory things at the exact same time? Photons, the fundamental particles of light, embody this intriguing paradox by exhibiting both wave-like and particle-like characteristics simultaneously. This remarkable property is known as wave-particle duality, a cornerstone of quantum mechanics. The why behind this duality lies in the very fabric of quantum reality. When we observe photons, their behavior seems to depend on the type of experiment we conduct. In experiments designed to detect particles, such as the photoelectric effect where light ejects electrons from a material, photons act like tiny, discrete packets of energy. However, in experiments looking for wave phenomena, like the double-slit experiment where light passes through two openings, photons create interference patterns, a hallmark of waves. It is not that they are sometimes one and sometimes the other, but rather that their full nature encompasses both aspects, revealing one or the other based on the interaction. So, how can we conceptualize or observe this? Consider the famous double-slit experiment. If you fire individual photons at a screen through two narrow slits, you would expect two distinct bands if they were just particles. Instead, an interference pattern forms, as if each photon traveled through both slits as a wave and interfered with itself. But if you place a detector at the slits to see which path each photon takes, the interference pattern disappears, and you observe two distinct bands, as if the act of observation forces them to behave as particles. This illustrates the profound influence of measurement on quantum systems. This concept was formally articulated by Niels Bohr as the complementarity principle, stating that these wave and particle descriptions are not mutually exclusive but are complementary aspects of the same reality. From the perspective of quantum field theory, photons are understood as quantized excitations of the electromagnetic field itself, meaning the field exists everywhere, but its energy manifests in discrete photon units. This offers a deeper insight into how both continuous field properties and discrete particle properties can coexist. Understanding wave-particle duality is not just an abstract philosophical exercise. It is absolutely fundamental to comprehending how the quantum world operates and how we design and build quantum technologies. It helps us appreciate that light, and indeed all matter at the quantum scale, behaves in ways that defy our everyday classical intuition, paving the way for innovations in fields like quantum computing and quantum communication.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.